Okay, so section 5.4, efficiency, energy sources, and energy conservation. This is a great picture of the Earth from space, and you can see where a lot of light pollution is given off. You can see those are normally the heavily populated areas are on the planet, so have some fun looking at that. It's a kind of a neat image. Because the last lesson was quite long in terms of time, I'm going to do this one a lot quicker today and give you a bit of a break. So we're going to talk about this word efficiency. Okay, so different things are rated in our homes, light bulbs in particular. If you've seen an incandescent bulb, that's the really, really old bulbs that have the wire that goes across. If they had 100% electrical energy going in, you'd have like 5% useful radiant light energy coming out, and 95% would be turned into thermal energy. So that's stuff that you could, if you've ever seen restaurants where they have big bulbs sitting over top of food, so much we call it heat or thermal energy is given off by those light bulbs that they can keep food warm. So they're no longer sold, as near as I can tell. We've moved from compact fluorescence, which is a CFL bulb, to LED bulbs. And I apologize, my stats are a little bit old at 2014, but they've all come down in cost a great deal, and you can pretty much buy LED bulbs for a lot less. Anyways, not to digress, let's get to efficiency. Very simple calculation. So efficiency equals the energy out divided by the energy in times 100%. Okay, and it's really important to understand this concept. There is nothing on Earth, in our solar system, anywhere that can output more energy than it takes in. It's impossible. If you ever figure it out, please tell me. We'll go be really rich together. But there is nothing that gives out more energy than it takes in. Okay, it's impossible. So all of your efficiencies, you will expect to have values that are less than 100%. Okay, so let's take a quick look at two here. So here's a firefly. So a firefly's body transforms chemical energy in food into radiant energy that appears as a greenish glow in its abdomen. So fireflies use this glow to track mates, prey. Who knows what else to do? Maybe they have parties with it. But what is a firefly's efficiency if its body transforms 4.13 joules of chemical energy into 3.63 joules of radiant energy? Okay, so if we set this up, we're already expecting we can't have a value greater than 100%. So if you're trying to figure out the efficiency, you don't have to memorize formulas. If you want to, you're welcome to. But here we know that it's going to give off 3.63 joules. Okay, it's transforming 4.13 joules into 3.63 joules. Okay, so when we do that, if we punch that in really quickly, we can see that this firefly transforms energy with an efficiency of 88%. That's it. That's all the calculations. So the hardest part in this section is determining what energy is in and what energy is out. Okay, so again, keeping in mind out is on the top, in is on the bottom. Again, it doesn't really matter because you're going to expect every answer to be less than 100%. Okay, so here's a quick one. What is the efficiency of a rope and pulley system if a painter uses 193 kilojoules, okay, of mechanical energy to pull on the rope and lift a 20 kilogram paint barrel at a constant speed to a height of 7.5 meters above the ground? Okay, so this is going to be your in. This is what the person's putting into the system. Okay, and then we're going to see what we get out of the system. So let's do the paint barrel. You could say that has an FG, mass times gravity. Okay, so mass is 20 times 9.8. That's 196 newtons. If we look at the work done, that's force times distance. 196 times, how far did they lift it? 7.5 meters. Give myself a little bit more room. That's 1,470 joules. So if we want to do our efficiency, okay, I want to have 1.93 is the bigger number. So I need 1470 on the top, 1930 on the bottom. So if I divide those out, I should get about 76% efficiency from this system. Okay? Alright, so pause it here and try a couple. These are right out of your textbooks if you want to pause it, and then we'll try and take a look at how the solutions came about. Okay, so a forklift uses 5,200 joules of energy to lift a 50 kilogram mass to a height of 4 meters at a constant speed. What is the efficiency of the forklift? So for number one, we have a force of gravity we're going to balance. That's 50 times 9.8. That's 490 newtons. I'm going to apply that 490 newtons over a distance of 4 meters, and that's going to give me my energy of 1960 joules. Okay, I have 5,200 joules of energy that went into the system, so my efficiency should be 1960 divided by 5,200. And I should get about 38% efficiency. Okay, and there it is. Okay, so second question, a tow truck. A tow truck attaches a cable to a car stuck in a muddy ditch. The 1,250 kilogram car is pulled up an embankment to a height of 1.8 meters at a constant speed. The cable exerts a force of 5,500 newtons over a distance of 12.6 meters to pull the car out of the ditch. Okay, so what is the amount of useful energy produced? Let's get a pen going here. So we have a tow truck, 1,200, that's if I need a picture. Okay, so I have my car, it's pulled up an embankment to a height, it's going to have a change of 1.8 meters at a constant speed. So we could say the work done to raise that car is the mass times gravity times the change in height, which is 1.8 meters. 9.8 times 1.8. So there's 22,050 joules. Okay, so the cable exerts a force of 5,500 newtons over a distance of 12.6 meters. Okay, so that's our next piece. Switch over, give myself a little bit more room. So now the cable, force times distance, that is 5,500 times 12.6. 69,300 joules. Okay, so I just did a little bit of quick calculation. So what is the amount of useful energy produced? Okay, so 22,000 is the amount of energy produced. That's what actually lifted the car out of the ditch. So we have that. That's pretty good. What amount of energy is used to pull the car from the ditch? That's our 69,000. Okay, right there. So if we want to do the efficiency, we just have to do a quick division of those two. So our efficiency, let's do it in red, would be 22,000 over 69,000. I got an extra zero there, my apologies. There it goes. And I should get an efficiency of 22,050. I'm going to use all my numbers because I have them. 69,300. 32% or thereabouts. Okay, so 32%. And again, notice I didn't spend a lot of time thinking about in and out energy. I simply know that the smaller number has to go on the top because I can't have a system that produces more energy from nothing. Okay, so there's 3 questions to try, 5.4, 1, 2, and 3. Thanks for watching. If you get a chance to download the PDF, there's a whole bunch of extra slides in there talking about hydroelectric, LEDs, things like that you might find really useful. I'm going to let you read it because it'll just take up lots of time, and I had a really long video on the last one, so I will trade off and pass this off to you. Thank you.